All right, so this is the first of a few lessons from Chapter 8, which finishes our work with linear systems. Essentially, in Chapter 7, we were introduced to what a linear system was, which is essentially more than one linear function at once, and what the solution of a linear system means, which is where you can visualize is where two lines intersect. Chapter 7 was mostly a graphical approach to things. There's lots of graphing of lines, sometimes including using Desmos. This last chapter in this big unit is looking at the same ideas, but from a purely algebraic standpoint. And so this set of notes, like all the notes in this short chapter, are almost all just best to be done on lined paper. I don't have a booklet for you like I did for other sections, because honestly, to record these notes, you want lined paper, not blank paper. So I start with this. I want to solve this system. I want to find where these two lines intersect. I want to solve for a and b in this case instead of x and y, but algebraically. And today's lesson, I want to focus on how to solve it, what we call it, using a method called substitution. The next lesson will be a different method called elimination. They can both work. They both have the pros and cons. But let's look at this first. So using substitution, the idea is I want to first isolate one of the variables. And there's four to look at. You know, I have two a's and two b's. So I got to pick one that I think is just personally feel is easiest to isolate. I can isolate any of them. I can solve for either a or b in any equation. But I want to do what is the least amount of work. Just for the simple reason it's less work, and I feel a bit lazy, and it's also, that means less chance of making a careless mistake. So I'm going to solve for b in the first equation. Although it would be just as easy to solve for a in the first equation. If I want to solve for a or b in the second equation, it would be a bit more work because I have to at some point divide by 5 or divide by 3. So all I want to do here is subtract a from both sides from the first equation. And so this first equation becomes b equals 22 minus a. OK, so what's the point of that? Well, the point of that then is I want to substitute 22 minus a for b into the other equation. So if you look in the other equation, there's a b as well. So I literally want to substitute that b with 22 minus a. And so the second equation now becomes 3a plus 5 times, instead of b, 22 minus a equals 95. Now notice, while I have a somewhat messy equation, it's nothing too crazy, it has just one variable, which means I must be able to solve for a. And so now, algebraically, I want to solve for a. The first thing I want to do is distribute the 5. So you get 3a plus 5 times 22 is 110, minus 5a equals 95. Next, I want to combine like terms. I'll combine my two a's together. So 3a minus 5a is negative 2a. And I'll just leave the 110 here for now. Then I'm going to subtract 110 from both sides. So I got negative 2a equals 95 minus 110 is negative 15. And finally, to figure out just a, I need to divide both sides by not 2, but negative 2. And so on the right-hand side, negative 15 divided by negative 2 is a positive number. 15 divided by 2 is 7.5, or 15 halves, but I'll go with 7.5. All right, so now I know a. I know one of my two values. If I visualize these as lines with an a-axis and a b-axis, I know my a coordinate. So I've done a fair amount of work, not a ton, but a fair amount to get one of my variables. The good thing is to find my other variable, it should be now very, very, very little work. So the idea is now that I know that a is 7.5, I can go back to any of these equations here, here, or here. And anywhere I see a b and an a, and substitute 7.5 in for a, and then I can figure out b. The easiest equation to use by far is this one right here, because this equation is already set up to tell me b exactly if I know what a is. The other equations, I have to do a bit more algebraic work. So I'm literally now going to take that 7.5 and put it back into there. And I'll know b, and I'll be done. So I'll say b equals 22, instead of minus a, minus 7.5. And 22 minus 7.5 is 14.5. And so now I know a and I know b. Notice how quick it was for me to figure out b once I figured out a. And so just to make my solutions really clear, I'll say a equals 7.5, b equals 14.5. If I want to write this as an ordered pair, it's not really clear what my x and y are. By general convention, just kind of go in alphabetical order. So I could say 7.5, 14.5. but I don't even know what A and B stand for. So it's hard to know what's your independent variable, what's your dependent variable. And so if you're not sure, just go with that. All right, so I can apply this to any system. Any system we've worked with, we can solve this way. Sometimes it's fairly tedious, and that's when it's a fair amount of work just to isolate A or B in the first place. Notice for this first example right here, it was one step to isolate B, and so it was a pretty good use of substitution. And we'll see in the next lesson a different method that's more useful when it's not so easy to isolate one variable so quickly. But that's it. Let's look at this example with decimals. Okay, again, I want to solve for either A or B. And eventually I want to know what A and B both equal. I need to pick an equation that is, I think, fairly easy to solve. I'm going to solve this B in the first equation. Although it would be just as easy to solve for A in the second equation. But I'm going to solve for B in the first equation, and to do so I'm going to subtract 2A from both sides. And so now that first equation I'm going to rewrite as B equals negative 4.2 minus 2A. All right, so now I want to take that and substitute it into my other equation. Wherever there was a B, I can now think of it as negative 4.2 minus 2A. So we've got a lot of negatives here, so I've got to be careful. But essentially the same steps as before. This is no harder than the last question, aside from there being decimals, but you're allowed to use a calculator. And so distribute to negative 3. So you've got to be careful here. I got 12.6 plus 6A, right? A negative times a negative. I'm going to combine my like terms together. 6A and A makes 7A. Add 12.6 to both sides. Definitely a calculator makes us a bit more confident with our calculations here. I get negative 17. Hold on here. I made a mistake. I just realized. And I apologize to anyone who saw the mistake and got frustrated. My mistake is right here. I want to distribute a negative 3 times negative 4.2. A negative times a negative is a positive. So that should be a positive. That should be a positive. Which means I should be subtracting each of these. There we go. And so that changes the step here. Yeah, negative 4.9 minus 12.6 is even more negative. It's negative 17.5. And then lastly, divide both sides by 7. So notice, like before, it took me a fair amount of work to get A. Not a crazy amount, but a fair amount. I got negative 2.5. Right, so that's A. And now it should take me very, very little work to figure out B, as long as I'm, wise, as long as I put some thought into what equation I put it back into. Again, I can go back to any of my original equations, and I can substitute any of these A's with negative 2.5 to figure out B. The easiest one is definitely going to be, again, the one I rearranged in the first step. And so I'm just going to take that negative 2.5, put it right there, and I'll have B. And so B will equal negative 4.2 minus 2 times negative 2.5. A lot of negatives here. But you can do that all on a calculator should you wish, and you just get 0.8. And so B equals 0.8, A equals negative 2.5. I'll just kind of write it formally down here. So A equals. There's my answer. Notice, just like before, in fact, every single time you work with substitution, if you do it properly, it should take you by far most of your work to find just one of the two solutions, and then it should take you like pretty much a single step to find your other solution. As long as you put into an equation that is, as direct as possible. All right, so for the last problem, I have going back to graphs, and this is the only part I believe is in that booklet. And I want to know exactly where these two lines intersect. And so I want to know the exact coordinates of that. Now, if I look at this, I can estimate this. I can see it's about, 2.6-ish right here, and about, sorry, that's a pretty bad estimation, 3.6-ish right there, and like 2.1. Okay, that's my estimate of where they intersect. I want to know exactly. Okay, so that's it. I know my answer should be around 3.6 and 2.1 if I decimalize them. So how can I figure out exactly where they intersect? Well, first thing I'll probably want to do is find the equations of my two lines, in which, the way I gave you the information here, it's probably easiest to do in slope-intercept form. If I look at the equation in blue, I can see the y-intercept is 1, and I can see the slope is up 1 over 3. So I can see the equation of my line in blue is going to have a slope of 1/3. So 1/3 x plus 1. That's the equation of my line in blue. And so for my line in red, same idea. I can see the y-intercept is down here at -5. I'll pick this point as well. I can see I go up 2 over 1. So this is the slope of 2 over 1. So the equation of this line is 2x minus 5. All right, so now I want to take these two equations and I want to solve that system. And I want to solve, using substitution. That's all we've learned about so far. The good thing here is that both of my equations already are solved for the same variable. This equation here is solved for y. This equation here is solved for y. So it's actually really pleasant to put these together. I can just take either of these, 1/3 x plus 1, and substitute it with that right there. Or I can take 2x minus 5 and substitute it right there. It's all the same thing. Because they both solve for y, I can essentially just put these two equations together right away. And so right away I can just say that 1/3 x plus 1 must equal 2x minus 5. And I can do that so quickly because, again, each of the equations was already solved for a variable. And so I can just put them together. And so now, again, I want to solve this. I have a fair amount of ways I could approach this. The first thing I want to do is multiply both sides by 3 to get rid of that fraction. So I'm going to triple everything. And so 1/3 x times 3 is just 1x. 3 times 1 is 3. And the other side, triple each of these, you get 6x minus 15. All right, so now I'm going to be done pretty soon. I'm going to subtract x from both sides. And I'll do it just one step at a time. So I get positive 3. I don't need the plus sign, actually. Equals 5x minus 15. I'm going to add 15 to both sides. 18 equals 5x. And so now I can see my x coordinate if I divide both sides by 5. 18 divided by 5 is 3.6. Hey, that's what I estimated. And so now I know my x coordinate. I can now substitute it into either of my first two equations because they're both solved for y. I'm going to choose the one I drew in red because there's no fractions. So I'm going to take that 3.6 and I'm going to put it right there. And so my y coordinate, I'll say, therefore, my y coordinate is going to equal 2 times not x, but 3.6 minus 5, which is 2.2. And my estimate was 2.1. So, those are estimates. So I know my answers are, they seem right. If I got an answer, for example, if one of my values was negative, I know I made a mistake because I can see the quadrant my solution's in. And so I'll just formalize it as an ordered pair. So I'll say the solution, or the intersection is, that's a weird looking is, let's try that again, is at 3.6 comma 2.2. All right, now every single system we looked at in the last chapter can be solved this way. Some, this is quite quick, some not so much, which is why there's another method we'll look at in the next video. And then ideally you can kind of choose between what you prefer depending on a particular question. And that's it for this.